It's very strange and have prevented me from sleeping. So I've kind of running on vapors here, and to run a lab with 1,000 conversations seems much less feasible than to run a review session where we're having a few conversations at once. So apologies for the change of plans, but I think this should go well and hopefully be very useful. By the way, I'm going to pass around the TBA sign-up sheet. If you are not up to date on that, please get that up to date. I know there's a few people who are not here today and weren't in lecture this morning who also have missing TBA hours, but at least we will be able to get 95% of the records up to date, and I can track down the stragglers on Monday. All right, so pass that around. So I can either take questions or I can start throwing out problems, which sounds like the best way of doing this.
Can we maybe talk just like generally about the exam first?
Generally about the exam?
Yeah.
Yeah, I mean, generally it will be the easiest of the exams. So, and the reason for that is that it also has to be the shortest. This time we can't take 3 hours and 45 minutes. We've got 2 hours and 50 minutes. And I know that last time, even when I was trying to write what I thought was a shorter exam than the first one, it didn't work out that way for a lot of people. So I will err on the side of trying to keep the exam as brief and to the point as possible. Yes?
It is cumulative.
It is cumulative. Now, you'll see as we're working through sample problems today, a lot of the cumulative, since I am trying to keep it short, I probably won't be saying, can I just write a problem that, just goes back and is a review of the things that we did at the beginning. Instead, I will try to incorporate the early things into problems that we're asking. So since electromagnetic induction, number one, it relies on changing B fields. So there will be a lot of, you need to be up to date on how B fields are created and how I can make one change. And number two, since electromagnetic induction creates induced voltages, what does an induced voltage do? It does exactly the same thing that would happen if I hooked up a little battery. So, that gives me a chance to go back and do Ohm's law and early things like that. In fact, as we're walking through problems today, I will probably in several places say, hey, one variant I could do here is, maybe I tell you this is made out of copper and I give you the resistivity and you find the resistance from that or something. So, there will be lots of ways that we can get cumulative stuff in there, but I won't be devoting entire problems to review just because, again, I'm already going to find, oh man, I want to ask about a lot of things, but I've got to keep this brief enough that I don't want time pressure to be an issue. I never want time pressure to be a huge issue on any exam, but since on this exam we've got kind of a finite time length, and some people, just out of curiosity, not that I will suddenly make the exam longer if nobody raises their hand, but how many people have a 10 a.m. final on Monday?
What?
Okay, so well, no, we have a 7 a.m. final on Monday, but how many people also have?
Wait, 7 a.m. Oh, fuck.
Yeah. So since there are people who need to be out of here at 9:50 on the dot, this exam will be shorter than the others, and in a sense more straightforward, just because I got to get right to the point. All right. Any other topics you want me to make sure to hit?
No, it's allowed, right? Like the previous exam, we only have an equation sheet.
Yeah, just an equation sheet, no notes. The equation sheet, the only things that we have really added to the equation sheet, obviously I'm not going to be putting vector calc identities and all that kind of thing on there. Frankly, the main things that we have added to the equation sheet are the frequency of an LRC circuit, the reactance of both a capacitor. None of these pins work. The reactance of a capacitor. Hey, by the way, a capacitor. Does the reactance go up with frequency or down with frequency? Down. A capacitor at real high frequency acts like a short, because you'd say every time I start to charge up one side of the capacitor, I immediately reverse the current to discharge that side. So a capacitor at real high frequency, you never build up very much voltage drop across it. So it's almost acting like a wire. Yeah. So yes, with a capacitor, even if the equation sheet's absolutely illegible, and I've lost my mind and I'm refusing to tell you the answer for the reactance of a capacitor. You know that reactance of a capacitor goes down with frequency. The reactance of an inductor goes up with frequency. If I try to send a high frequency current through an inductor, even if the current has a pretty low amplitude, I'm going to get a lot of induced voltage. And of course, you know, in the same way that Ohm's law says the voltage drop across a resistor is IR, the version of Ohm's law for impedance says the amplitude of the voltage drop. What I mean by that, not in this case, isn't initial, but I mean the amplitude. The amplitude of a voltage drop across any of these devices goes as the amplitude of the current times the impedance. So the only difference between those two rules, Ohm's law applies instant by instant. At an instant when the voltage is at a max across a resistor, the current is also at a max. These things apply across a whole cycle. If I wait through a whole cycle and say what was the maximum voltage that I hit, and then I also wait through that whole cycle and say what was the maximum current that I hit, they won't happen at the same time for an inductor or capacitor. For a capacitor, you tell me, for a capacitor, voltage leads or voltage lags? Voltage lags. And again, it's because for a capacitor, the current needs to have already been flowing to charge up that plate, and then you'll be seeing a high voltage. For an inductor, on the other hand, voltage depends on di dt. It depends on the rate of change of the current. So you'd say if the current is changing rapidly, if it's progressing toward a maximum, that could mean the voltage is already at a maximum when the current is at its fastest change. So yeah, for a inductor, voltage leads. For a capacitor, voltage lags. You can do the Eli the Iceman thing, but I've once again forgotten how the hell the Eli the Iceman thing is supposed to work. But I can't tell you just physically, if you think how those two devices work, yeah, capacitors live in the past, inductors live in the future. Resistors are Zen-like. Resistors live in the present, and whatever the voltage is right now, that's going to tell you what the current is doing right now. So there are some new things that you'll have on the equation sheet. Of course, you will have Faraday's law, which is telling you that either I could write it this way, I could say the integral of the E field around some closed loop is the integral over the surface bounded by that loop of dB dt. Or I could say the induced is the rate of change of the magnetic flux through that loop. And those are just kind of two ways of saying the exact same thing. In fact, you could say a third way of saying the exact same thing now is just saying the curl of E is minus dB dt, because that statement, together with the curl theorem, Stokes theorem, or whoever's name we put on it, gives you that statement. Now, as far as new physics, yes, I'll be asking you some stuff about the LRC circuits, but I'm going to be focusing mainly, especially because I feel like, oh man, I don't have as much time to ask about everything I wish I could. If in doubt, I'll be focusing mainly on the fields. I'll be focusing mainly on the electromagnetic induction. So let me give you a problem there. Let me say we have got a region with a uniform B field. And it is pointing into the page. So all through this region, we're suffused with this B field that points into the page like that. And I want to give an electromagnetic induction problem. If I want to give an induction problem, the flux has got to be changing. What is my definition of flux? I suppose this belongs on the equation sheet also. I have to say, by definition, flux is just the integral of the B field, dotted with that perpendicular area vector through whatever surface I'm dealing with. Or if the B field's uniform, flux is just B field times the area of the loop times, and again, that dot product tells me, oh yeah, I should put in a cosine of some angle, a cosine of the angle between the B field and the normal to that area. So I already said the B field's uniform, but the B field could be changing. So if I want to deflux dt, there are three ways I could make that happen. I could let that B field be changing, and even though I've said it's uniform, that means it's uniform with space. I haven't said yet whether it depends on time or not. I could let the area be changing with time, or I could let phi be changing with time. Let's run one of each. Suppose I want the area to be changing. Those are usually things where either I've got a loop that I'm dragging in and out of this region of B field, or I've got one of those fun little railroad problems. Let's do a railroad problem, and in fact, let's do this. I'm going to set this up in a gravitational field. So I make one of those area changing railroads. I've got a bar across the top. I'll just say those are all perfect conductors. And I've got this movable crossbar. The movable crossbar, I would either give you its resistance R, or if I felt like it, how could I kind of have you do a step or two to get the resistance R? Yeah, I mean, I suppose I could just tell you everything else about the problem that you solve for R at the end, but I could also tell you, oh yeah, it's made out of material with resistivity rho, and it could be copper, it could be graphite, it could be glass with very high resistivity or whatever. But yeah, one way that you could get that R would be, I might tell you rho, and I might tell you the length of the rod, which I'm going to need to tell you anyway in order to set up the changing flux, and either tell you it's a circle or a rectangle or whatever in cross section, but this would be the cross sectional area, or I could just give you R either way. And what I'm going to do is I'm going to actually set this in a gravitational field. Let's say that G is pointing straight down the page like this, and we drop this rod. We let it slide downward without friction. So it's moving downward at velocity v, and we will let it accelerate. I could ask you what will be the terminal speed that that thing hits, at which point it'll just be falling without accelerating anymore. Is the first thing I could ask is, why the hell will it have a terminal speed? We're used to things having terminal speed because